This is the 15th lecture in the Fiber Optic Association lecture series on fiber optics. In this lecture, we're going to talk about testing fiber optic cable plants and 5 different ways you can test them. How do you test fiber optic cable plants? Well, industry standards around the world include 5 different ways you can actually do the tests. And those 5 ways will give you 5 different results for the loss of the cable plant. 3 of them involve insertion loss using a light source and power meter, and 3 different ways of setting the reference for 0 dB. Then there are 2 separate ways of using an OTDR to test the cable plant loss. So let's look at all of these. The first 3 methods are insertion loss tests. Insertion loss tests use a light source and a power meter and test the cable plant very much the same way as a communication system uses the link, where a source puts light into one end of the cable plant, and as the signal goes down the fiber, it's attenuated by the attenuation coefficient of the fiber. It will lose power at a connection or a splice, and then continue losing light due to the attenuation of the fiber until it reaches the receiver. All insertion loss tests work basically the same way, but the difference is how you set the reference for 0 dB. There are different standards for single-mode and multi-mode fiber, but the methodology is basically the same. We call this insertion loss test a double-ended test because we attach a source with a launch cable to one end of the cable plant and a meter with a receive cable to the far end. Because we're mating reference cables to both ends of the cable plant, we're able to test the connectors on the cable plant itself. Plus, we test for the loss of anything in the cable plant itself that causes loss. The real question arises is, how do you set the reference? And the reference for 0 dB is set in 3 different ways, as you'll see next. The first method uses a one-cable reference. We attach our reference cable to the source and then attach it to a meter and measure its output power. We then take the source and connect it to the cable plant we want to test at point A. On the other end of the cable plant, we attach another reference cable, we call it the receive reference cable, and we use that to connect to our fiber optic power meter. Since we know the output of the launch reference cable, we can measure the loss of the cable plant connection at A, any losses in the cable plant, the loss of the connection of the cable plant to our receive reference cable at point B. So our measurement includes the connections on both ends of the cable and everything in between. The problem with this method is it won't work with all cable plants. If, for example, the connectors on our cable plant are not compatible with the connector adapter on the meter, we won't be able to both make a reference and connect the reference cable to the cable plant with the same reference cable. This happens to work only with connectors that can be mated to each other and to the fiber optic test equipment we're using. If the connectors on our cable plant are different than the connectors on our instruments, for example, we're measuring LC cables with ST or SC meters and sources, we can use what's called a 2-cable reference. Here we use hybrid reference cables that mate to our instruments on one end and mate to the cable plant on the other. We make a similar kind of measurement, but with one major difference. When we have set the reference, we include in our reference the loss of the connection between the two reference cables. When we make our final test, the value we measure for the loss of the cable plant will be smaller by the loss of that connection between the two reference cables. Sometimes, not only will the connectors on our cable plant not mate with instruments, but they won't mate with each other. For example, with duplex or multi-fiber male-female type connectors like the MTP or MTO. Then we can use a 3-cable reference. Now we use a launch cable on the source, a receive cable on the meter, and a third reference cable in between the two, which is our stand-in for the cable plant. And that third cable should be a low-loss cable. So we merely make the reference, take it out, and then attach our cable plant. But the problem is, this time we have 2 connections when we make our reference, and the cable plant loss will be reduced by the amount of loss in those 2 connections. Here's how our measured value of cable plant loss will differ with the 3 different methods. With the 1-cable method, we have no connections in our reference measurement, so we measure the actual loss of the cable plant, including the end connections. With a 2-cable reference, we measure the same loss but less the value of the connector when we made our reference measurement with 2 cables. With a 3-cable reference, we get the same loss for the cable plant, but it's less the value of the 2 connectors loss when we set a reference. Because we have these unknown connector losses when we make our measurement, it affects the loss error. So we have a relatively small error with a 1-cable method, but a relatively large error when we do a 3-cable reference method. The next 2 methods use OTDRs. OTDRs don't test like the system uses the cable plant or like an insertion loss test. They use backscattered light to take a snapshot of the cable plant and calculate what is a projected loss value for the cable. 2 methods are used. The traditional method takes a launch cable, which also allows the OTDR measurement to settle down before you make a test, and connects it to the cable plant under test. The OTDR will then calculate the loss of the connection of the launch cable to the cable plant under test and the entire length of the cable plant less the connection on the far end, which is open, not connected to anything. The second OTDR test method adds a receive cable on the far end of the cable you want to test. Now we have the cable we want to test connected to both a launch cable and a receive cable. We can then measure the connection to the cable under test, the loss in the cable under test, and the far end connection. So we get a more accurate view of what's actually going on in the cable plant. However, we still have the problem that the OTDR test is a calculated test, not a direct test of loss. And the likelihood of a test with an OTDR agreeing with an insertion loss test is relatively small, depending on the test method we use and the length of the cable plant involved. So what's the right method? Well, there really isn't a right method. Each of these has their own use. Insertion loss mimics the cable plant use, and it allows correlation of your measurement to the loss budget. But you have to make a correction for the method you use for setting your 0 dB reference, because your loss budget will include the loss of the cable plant. But if you use a 2-cable reference, you'll measure 1 connector loss less than your loss budget, and with a 3-cable reference, you'll measure 2 connector losses less. You choose the insertion loss method that's basically required by the connectors that are on your cable plant and test equipment. The OTDR is really more often used for splice location and loss verification. You should not expect an OTDR to give you end-to-end loss that matches the actual loss the system will see on the cable plant. The amount of difference that you see will be a function of how long the cable plant is. If the loss is relatively low, a few dB, the difference will be less than if the cable plant loss is 20 dB. So generally speaking, you test with insertion loss to verify that the system is installed properly and will work with your communication system. And you test with an OTDR to verify that you've made splices properly, determine their location, save a trace so that later on you can refer to it for troubleshooting and restoration. So you see, the 5 methods all have their own particular usage and application. Be sure you see the other FOA YouTube videos, especially the other videos on testing, and refer to the FOA online reference guide for tutorials, virtual hands-on training in various processes in fiber optics, and even find an OTDR simulator, which you can use to learn more about how OTDRs actually work. We're the Fiber Optic Association, the Professional Society of Fiber Optics.